I recently made a level in GD that has what I like to consider as an AI. I'm making this video to help explain the massive amounts of design I put behind it and hopefully spark some interest in coding for both GD and actual languages. AI at its core is simply a program that gathers a lot of data and uses it to find certain criteria. In my case, it was the most optimal move in a game of tic-tac-toe. I chose tic-tac-toe because of its relative simplicity, as well as not requiring a massive amount of data to solve the most optimal move. That said, making this project was very difficult and I myself found it very fun to make. A note before I begin explaining. I'll be using some advanced trigger concepts, and if you don't know anything about it, I'd recommend learning before you try to build something similar to this. Before I made this level in GD, I actually programmed this exact thing in Java and ended up porting over 950 lines of code into triggers. Knowledge of coding is very helpful for learning how to do more advanced trigger math, and with that, let's begin. The first thing I had to do before I made an AI was make the actual game itself, of course. This was no easy task, and I tried to make as many of the parts of the game as modular as possible, so I could easily plug them in for the AI for smooth integration. This ended up being very helpful, as well as saved me a lot of time, showing the value of proper pre-planning. I believe the most important example of this integration is when I created the triggers that handle the placement of an X or an O onto a certain part of the grid. The code first checks if the space is available. If it is, then it gets the current player and places the respective icon, then switches to players. I could explain every part of this game's code, but that isn't why you're watching this video most likely. This AI took by far the most triggers and work to create of this entire project. Understanding data is very important for projects like this, so I had to devise my own system for how the program will read the current game data. To win tic-tac-toe, you must have 3 in a row. There's 8 possible wins, so the AI must scan 8 different things. I like to call each line you can win on a thread. Threads 1 through 3 are horizontal, 4 through 6 are vertical, and 7 through 8 are diagonal. I didn't really know where to begin to start building the AI, so at first I devised a simple system that finds the first available open spot going from left to right to make sure everything was working smoothly. The system turned out to be extremely important to the system later on. This is where things start to get a bit complicated. I tried to mimic human thought as much as I could with this AI, as well as establish an order of operations for the AI to follow, so I created this poorly drawn diagram. The AI will first search if it can win in one move. If it can't find that, it'll search for if the other player can win in one move. Then it detects if it can get 2 in a row, and then if it can't, it just places a random block. After that, I had to conceptualize how the AI would even recognize data that would pass certain tests. To do this, I gave each thread a variable, and each scan would change that variable. Let's take thread 1 for example, scanning for if the AI can win in one move. The AI checks each of the 3 slots for who owns each box. If the AI owns a box in a thread, it increases the thread value by 1. To win, the AI needs 3 in a row, so 1 slot must be open and 2 must be owned by the AI. If the player owns a space on the thread, I needed to render it unusable so it would be skipped, so if a player owned square was detected, the value decreased by 3. Converting this into triggers, I keep my code well formatted with arrows so it's easy to follow. Starting at the left, each of the clusters of instant counts checks for who owns each position of the thread, assigning appropriate values. After scanning, the system checks the thread value. If it's equal to 2, it then locates the open space and places an X. If the value is not equal to 2, it moves on to the next thread because it doesn't meet the criteria. I was quickly able to design clusters of these thread scanners, and very soon it was able to scan each of the 8 threads for a single criteria, that being whether or not it could win in one move. Of course, this was still far from a good AI. At this point, it could either place random blocks sequentially, and also could detect if it could win in one move. After making this, I needed to clear out the previous scan's data so that it would not be corrupted and give inaccurate readings each time, so I made a reset system that clears out all the thread values as fast as possible. Fun fact, when you're playing the level, the majority of the time spent waiting for the AI to calculate is simply buffer, waiting for the reset to conclude. From this point on, I had a reliable system for scanning the board for specific things. I just needed to continue adding more scans for different things. The next progression on the AI was to scan for if the player had one more move left. This was very easy to make, and it was simply just the previous code but with the players flipped. So for example, if it detected an AI owning a spot on the thread, it subtracted from the value, skipping it. It's actually kind of funny. As I sit here recording the voiceover, I realize I could have made the system more efficient by repurposing the first scan to detect both criteria at once, saving hundreds of triggers. This is why I love programming in general, because there's always room to improve. The third scan was very annoying to design because I had to redesign how this part placed the blocks quite a few times. This scan searched for if the AI could get 2 in a row, so this time there was 2 open spaces. I ran into a lot of trouble with the AI detecting that it can get 2 in a row, then placing blocks in both of the open spaces, so I needed to add a delay for each time it tried to see if there was an open space, as well as added a variable to find if a block was already placed at AI round, so it would only place 1 block. Finally, all 3 criteria were met and constructed, so if the AI failed to find any of these 3 criteria, it still needed to place a block. Usually, this last part only triggered if it was the AI's first placement, so I wanted to randomize where it placed the blocks so it wouldn't follow the same pattern every time, adding some additional challenge and realism to it. This part saw more than 6 different redesigns, the reason being the AI would either not be random or would simply place a random block on top of a block the player already owns. Finally, I designed a system resembling a loop. The AI gets a random number between 0 and 8, each representing a square on the board and places an X there. If it detects the player owns that square, it moves to the next one next to it, and so on until eventually it finds an empty space. To make the numbers random, I actually use the loop that animates the cursor back and forth. It increases by 1 every second and rotates through those numbers infinitely until the AI needs to randomly select a number. It gets the number that is looping and places. If you somehow played exactly the same way, the same speed, and had perfect luck, the AI would play the same way every time. This obviously will never happen, so I just left it as it is. At this point, I had a working AI that could play tic-tac-toe against you relatively well. If you haven't given the level a try, I implore you to go try and beat the AI. It's harder than you think. Obviously, it was far from perfect. Occasionally, it would make a less than optimal play, but I just pass it off as it's making a simple user error, partially because I wanted human thought, and because I'm lazy. If I turn on the debug mode in the finished version, you can see all the variables changing as the game is played. The numbers on the left are each thread variable as the AI scans. Notice how fast it scans, clears, and rescans? See if you can guess what any of the other variables displayed on screen are. They're all used in the core of the game's processes, and there was a staggeringly high amount of them that were being managed at any given time. All that was left to do now was to decorate and make sure everything was working well. I always loved getting glitches where the game would begin to loop the AI, so the game would start to play itself versus itself. It was very intriguing to watch, but would almost always end up the same way. I fixed as much as I could, and then, after over 20 hours of work, my program was complete. I hope this video gave you some insight into just how much work goes into things like this. Imagine making an AI for a game with hundreds of rules, like chess. Hopefully I sparked some enthusiasm for people interested in getting into coding, especially AIs. I'm very passionate about this stuff, so I'd be very happy to see some other people sharing my enthusiasm. I invite anybody to crack open my level and make it more efficient, or even design their own AIs. I'd love to see people push the limits further and further. This was a different type of video than what I usually put out, and if you liked watching it, let me know and I'll be sure to make more informative videos like this one. My aim is to inspire others to make great things. Thank you for watching. My channel would be nowhere without you guys.